There is a moment, roughly 24 hours into the Artemis II mission, when the 4 astronauts aboard the Orion spacecraft will be further from Earth than any human beings have been in over 50 years. They will be alive. They will be breathing recycled air inside a pressurized capsule the size of a large SUV. They will be in communication with Mission Control in Houston, and engineers on the ground will be watching every telemetry feed, every oxygen partial pressure reading, every thruster pulse, every heartbeat transmitted from inside those suits. Everything, by every measure, will appear to be going according to plan. And yet, if something goes wrong in that window, if a micrometeorite punches through the hull, if the life support system develops a cascade failure, if the propulsion stack loses its ability to orient the spacecraft for a return burn, there will be nothing anyone can do. Not the flight directors in Houston, not the engineers who built the capsule, not the crew themselves, because some failures do not leave survivors with enough time or resources to respond. The rescue infrastructure that exists for every other crewed mission in history, the abort modes, the launch escape systems, the quick return corridors, will not reach them. The physics of where they are going simply does not allow it. This is not a design flaw. It is not a failure of planning or political will or budget. It is a structural feature of the mission itself, baked into the orbital mechanics, the capsule's fuel budget, and the geometry of cislunar space. Artemis II is designed to go to a place where, for approximately 24 hours, rescue is geometrically impossible. The crew knows this. NASA knows this. And when you understand why and what that window actually means in the context of everything humanity has staked on this mission, the number takes on a weight that is very difficult to shake. 24 hours. It does not sound like much, a single rotation of the Earth, the length of one workday plus a full night of sleep. But in the context of this mission, that 24-hour window is the edge of a cliff that the entire human spaceflight program has spent decades deciding whether or not to walk up to. And in the early months of 2025, NASA made the decision to walk. To understand why that window exists, you have to understand where Artemis II is actually going, not in the vague, press release sense of around the moon and back. You have to understand the specific trajectory, the geometry of it, why that particular path was chosen, and what it means in terms of where the crew is relative to any possible help during each phase of the flight. Artemis II is a free return trajectory mission. That phrase is important, and it is worth spending time with, because it is both the thing that makes the mission survivable under most failure scenarios, and the thing that creates the rescue impossible window in the first place. A free return trajectory is a path through the space that uses the moon's gravity to bend a spacecraft's course back toward Earth, without requiring any additional propulsive burn. You fly out, you swing around the moon, and the geometry of the gravitational system brings you home. Apollo 13 used a free return trajectory to survive its oxygen tank explosion in 1970. The principle is the same for Artemis II, but free return trajectories are not magic. They are a specific deal you make with orbital mechanics. You get the guarantee of a passive return path in exchange for accepting a very particular set of constraints on where you can be, how fast you are going, and what options you have if something goes wrong at different points along that path. And one of those constraints is the existence of a window, not at the beginning of the mission, not at the end, but in the middle, where you are simply too far from Earth for a rescue to reach you in any medically or physically meaningful time frame, and too committed to the lunar flyby to abort back on a short return corridor. That window opens at approximately the 20-hour mark of the mission. It closes at approximately the 44th hour. At its deepest point, the crew will be somewhere between 230,000 and 270,000 miles from Earth, depending on the exact timing of launch and the precision of the translunar injection burn. The Moon will be ahead of them. Earth will be behind them. And the window in which a catastrophic failure becomes unsurvivable, not because of the failure itself, but because of the geometry of their position, will be fully open. To feel the weight of this, you have to compare it to what rescue looks like at every other point in the mission, because Artemis II does have rescue modes. It does have abort scenarios. The engineers at NASA and Lockheed Martin and every contractor who worked on the Orion spacecraft spent years designing abort systems into every phase of the mission. There is a launch abort system on top of the rocket, capable of pulling the crew capsule away from an exploding space launch system in the first several minutes of flight. There are abort modes during the first phase of ascent that would put the capsule on a return trajectory within hours. There are abort modes during the early translunar coast phase that would fire the service module engine and curve the spacecraft back toward Earth on a fast return path. And there are abort modes in lunar orbit, if Artemis II were going into lunar orbit, which it is not. But in principle, that would bring the crew home within 2 to 3 days. All of those abort modes exist because at all of those mission phases, the physics cooperates. The distances are manageable. The fuel budget accommodates a corrective burn. The trajectory can be bent back toward Earth without requiring more than the spacecraft's available propellant. Rescue is not easy at any point in the mission, but it is at least geometrically possible. The rescue impossible window is the phase where none of that is true. It is the phase where the spacecraft is too far downrange for a short return abort. The Moon's gravity is not yet in a position to assist a return curve, and the available propellant in the service module is not sufficient to simply point the engine at Earth and burn home. If you tried to do that from the middle of the rescue impossible window with the fuel load Orion carries, you would either run out of propellant in deep space, or you would arrive back at Earth at a velocity that the heat shield cannot survive. The geometry of the situation does not leave a workable door. This is what mission planners mean when they talk about the concept of the abort boundary. Every crewed mission has abort boundaries, moments in the flight, where one mode of emergency return transitions to another. The abort boundary on Artemis II is not a gradual fade. It has a relatively sharp edge. On one side of it, the service module has the propellant and the time to execute an emergency return burn. On the other side of it, the spacecraft is committed. It will either complete the flyby and coast home on the free return trajectory, or it will not come home at all. The 24-hour rescue impossible window is not the entire mission. It is not even the majority of the flight, which is projected to last approximately 10 days from launch to splashdown. But it is the period during which the quiet arithmetic of deep space becomes, for the first time since Apollo 17 in December 1972, a real and present constraint on human survival rather than a theoretical one. And here is the thing that makes this different from Apollo, and different from everything that has come between Apollo and now. The International Space Station has been continuously crewed for over 2 decades. Every person who has lived on that station has lived within approximately 250 miles of Earth's surface, close enough that a Soyuz or a Crew Dragon can deorbit and land within hours of a declared emergency. The commercial crew program, SpaceX's Dragon capsule, Boeing's Starliner, all of them are built for low Earth orbit, where rescue is never more than a few orbits and a re-entry away. Every human being who has gone to space in the 50-plus years since Apollo has done so in an environment where Earth was close enough to reach quickly in an emergency. Artemis II is the first mission to deliberately leave that envelope, not because the program had to, not because there was no way to design around the rescue window, but because going to the moon, actually going to the moon in a way that matters, in a way that lays the groundwork for landing humans on the lunar surface, requires accepting that the distance is real and that the physics of that distance have consequences. The mission profile was chosen this way on purpose. The free return trajectory around the moon is the safest possible architecture for a first crewed cislunar flight. The rescue impossible window is the smallest it can be given the physics of that trajectory. The crew has been selected in part for their ability to function under conditions where no external rescue is possible. Everything about the mission design acknowledges the window and works around it as much as the laws of physics allow, but the window is still there. And understanding what it would actually mean for that window to matter, for a failure to occur during those 24 hours, requires understanding what the crew is actually doing during that phase, what the spacecraft systems are doing, and what specific failure modes become categorically unsurvivable in a way they would not be at any other point in the mission. The Orion spacecraft that carries the Artemis II crew is not the Apollo command module. It is bigger, heavier, more capable, and more automated. It carries more consumables. It has more redundancy in its critical systems. The life support architecture is different, drawing on decades of lessons from the Space Shuttle program and the International Space Station. The heat shield uses a new ablative material, AVCoat, applied in a different configuration than the original Apollo heat shields. The parachute system has been redesigned. The communications architecture is more sophisticated. By almost every metric, Orion is a more survivable vehicle than the Apollo command module was, but it is not invulnerable. No spacecraft is. And the failure modes that matter during the rescue impossible window are not the ones that Orion's redundant systems are best equipped to handle. They are the ones that are fast, catastrophic, and physics-based rather than mechanical. A micrometeorite impact capable of breaching the pressure vessel. A sudden and uncontrolled propellant leak that leads to an unplanned attitude change, spinning the spacecraft in a way the thrusters cannot correct before the crew loses consciousness. A failure in the carbon dioxide removal system that is rapid enough to overwhelm the backup before the crew can intervene. These are not the scenarios that dominate mission planning discussions because they are low probability. But they are the scenarios that the rescue impossible window makes definitively fatal in a way that identical failures at other mission phases would not be. A pressure vessel breach during the ascent phase, for example, would trigger the launch abort system. A breach during the early trans-lunar coast phase before the abort boundary would trigger an emergency return burn. A breach during the rescue impossible window means the crew is in a spacecraft that is losing pressure at a rate that may or may not be survivable 250,000 miles from the nearest help, with no possibility of an external rescue reaching them before the situation resolves itself one way or another. The mission planners know all of this. The crew knows all of this. Commander Reed Wiseman, who will sit in the left seat of Orion for the duration of the mission, is a former Navy test pilot who flew F/A-18S from carrier decks and then spent 5.5 months on the International Space Station, he has spent his career in proximity to the kind of failures that kill you quickly. He understands risk envelopes not as abstractions, but as lived professional reality. When he was assigned to Artemis II, he understood exactly what the Rescue Impossible window meant, and he accepted the mission anyway. That acceptance is itself part of the story, because the 24-hour rescue window is not just a technical fact about Artemis II. It is a statement about what humanity is willing to risk and why and on what timeline. It is a data point in a much longer countdown, one that began with the last Apollo mission over 50 years ago and is now, finally, ticking again. The question that Artemis II is really answering is not just, can Orion survive a free return trajectory around the Moon? The question is, are we willing to put human beings in a position where rescue is impossible? Because the thing we are trying to reach requires us to. The answer, as of the current mission planning calendar, is yes. And the 24-hour window is when that yes becomes real. To understand what the crew experiences during that window, not just technically, but physically and psychologically, you have to follow them through the entire trajectory from launch to the moment the window opens. Because the window does not arrive suddenly. It builds. The distance accumulates in a way that is perceptible to the crew, and by the time they are deep in the rescue impossible phase, the psychological weight of their position is something that no simulation, no training run in the neutral buoyancy lab, no mock-up in a vacuum chamber can fully replicate. They will be the first human beings since Gene Cernan and Harrison Schmitt to be that far from Earth. They will know it, and the 24 hours will pass in a capsule the size of a large SUV with the Earth a pale blue marble behind them and the Moon a grey-white mass ahead, and no one able to reach them, no matter what happens next. That is where we begin. The Space Launch System, the rocket that will carry Artemis II off the pad at Kennedy Space Center, is, by raw thrust numbers, the most powerful rocket ever successfully flown. It produces approximately 8.8 million pounds of thrust at liftoff, slightly more than the Saturn V that carried the Apollo missions, and significantly more than any other rocket currently operational. The comparison to Saturn V is not incidental, it is the entire point. NASA needed a rocket capable of sending a crewed capsule on a translunar trajectory with enough mass and propellant margin to make the mission survivable, and the Space Launch System was designed from the ground up to do exactly that. The launch window for Artemis II is constrained by a set of requirements that interact in ways that are not immediately obvious, but that have a direct bearing on when the Rescue Impossible window opens and what the crew's options are during it. The launch must occur during a window when the geometry of the Earth-Moon system is correct for the free return trajectory. The Moon must be at the right point in its orbit. The orbital plane of the trajectory must be oriented to bring the spacecraft back to a splashdown point in the Pacific Ocean where the recovery fleet can be positioned. The launch window, the actual number of minutes per day when liftoff is possible, is constrained by all of these factors simultaneously, and it can be as narrow as a few minutes. If the launch occurs at the opening of the window, the translunar injection burn, the burn that sends the spacecraft from its initial parking orbit to the Moon, happens at a specific point in the spacecraft's second orbit around Earth. That burn lasts approximately 6 minutes. It adds roughly 7,000 feet per second to the spacecraft's velocity, putting it on a trajectory that will carry it away from Earth at a speed that starts fast and gradually slows as Earth's gravity pulls back against it. At the moment of the translunar injection burn, the clock on the Rescue Impossible window effectively starts running. Not because the window opens immediately, it does not, but because the decisions made in that burn determine where the spacecraft will be at every subsequent moment of the mission, including the moment the abort boundary passes and the window opens. In the hours after the translunar injection burn, the crew begins what is called the translunar coast. This is the long, quiet phase of the mission, the crossing. The spacecraft is no longer burning its engine, it is simply moving, carried forward by the momentum of the injection burn, gradually slowing as Earth's gravity works against it, gradually beginning to accelerate again as the Moon's gravity takes over in the final hours of approach. The crossing takes approximately 3 days each way. The Rescue Impossible window occurs during the second half of the outbound translunar coast, the phase where the spacecraft is past the abort boundary and not yet in position for the lunar flyby. During the first half of the translunar coast, before the abort boundary, the crew has options. The service module engine is still capable of executing what mission planners call a PC+2 abort, a burn executed approximately 2 hours after the perisyntheon, the closest approach to the Moon that would loop the spacecraft back toward Earth. Before the spacecraft reaches the abort boundary, variations of this return burn are available at different propellant costs. The farther out the spacecraft goes before the abort, the more propellant the return burn requires, and the longer the return transit takes, but the option exists. The door is open. The door closes at the abort boundary. From that point on, the service module does not carry enough propellant to execute a viable return burn. The only path home is through the lunar flyby and the free return trajectory. The crew is committed. The window is open. What happens to the human body and mind during 24 hours in that window is something we will spend time with. But first, you need to understand the specific shape of the risk, not as a statistical abstraction, but as a sequence of moments, each one separated from the last by a decision that either maintains the spacecraft's survival margin or erodes it. Because the Rescue Impossible window is not uniformly dangerous. It has a shape. It has a deep point, a moment of maximum commitment, and an exit ramp that begins to appear on the far side as the lunar flyby approaches and the free return trajectory begins to reassert itself as a viable path home. Understanding that shape is the key to understanding what the crew is actually managing during those 24 hours and why the engineers who designed the mission made the choices they did. We begin at hour zero. Hour zero is the moment the Space Launch System clears the tower. Everything before that moment, the years of engineering, the budget battles, the 2 scrubbed launch attempts, the overnight in crew quarters at Kennedy Space Center, the suit up, the ride out to Pad 39B in the Astrovan, the climb up the launch tower elevator, the strapping in. All of that is prologue. The mission does not begin when the crew walks out of the operations and checkout building to applause. It does not begin when the countdown reaches T-10 minutes and the final automated sequences take over. It begins when 8.8 million pounds of thrust separate 5.75 million pounds of rocket and spacecraft from the surface of the Earth, and the vehicle commits itself to the sky. In those first minutes, the Rescue Impossible window is the furthest thing from anyone's operational mind. This is the phase of maximum acute danger, the phase where a single catastrophic failure would mean death measured in seconds, not hours. The launch abort system, the tower of solid rocket motors mounted above the Orion crew module, is armed and ready. It can pull the crew capsule away from a failing rocket in under half a second, firing at nearly 200,000 pounds of thrust to yank the capsule clear of the fireball and deploy parachutes for a water or land landing. The abort system has one job, and it is a brutal, violent, urgent job. This is not the contemplative danger of the rescue impossible window. This is the kind of danger that resolves itself in under 2 minutes, one way or another. The first 2 minutes are the solid rocket booster phase. The two massive strap-on boosters that flank the core stage produce the majority of the vehicle's lift-off thrust. They burn through their propellant in approximately 126 seconds, then separate and fall away into the Atlantic Ocean. The vehicle is now leaner, faster, still accelerating, with the core stage's 4 RS-25 engines carrying the load. The RS-25's engines, originally developed for the Space Shuttle program, refined over decades of flight, among the most reliable large rocket engines ever built, will burn for approximately 8 minutes after booster separation, carrying the vehicle through the period of maximum aerodynamic pressure, through the phase where the launch abort system is jettisoned, because the vehicle is now high enough and moving fast enough that a pad abort is no longer the relevant failure mode, and into the upper atmosphere, where the sky transitions from blue to black. At approximately 8.5 minutes after launch, the core stage engines shut down and the stage separates. The interim cryogenic propulsion stage, the upper stage that will complete the push to parking orbit and later execute the translunar injection burn, takes over, and the crew is in space. Not in the final configuration for the mission yet, but in space. The launch abort system is gone. The solid rocket boosters are gone. The core stage is gone. What remains is the Orion crew module and service module attached to the interim cryogenic propulsion stage in a parking orbit approximately 1,800 miles above Earth's surface. The crew has approximately 2 hours in this parking orbit before the translunar injection burn. This is not a rest period, it is a systems check period. Every critical system on the Orion crew module and service module is evaluated by the crew and by mission control. Propulsion, life support, power, communications, navigation, thermal control. The spacecraft that was folded inside a rocket fairing on the launch pad is now alive and working in the vacuum of space, and the first 2 orbits are the window in which any show-stopping problem has to be identified before the vehicle commits to going to the moon. This is the last point at which the mission can be called off at relatively low cost. If a critical system is degraded, not catastrophically failed, but operating below the threshold required for a safe lunar mission, Mission Control has the option of commanding a de-orbit burn and bringing the crew home on a routine emergency re-entry. It would not be a rescue in the dramatic sense. It would be a decision made calmly by flight directors and communicated to the crew to land earlier than planned. The mission would be over, but everyone would be alive, and the spacecraft would have demonstrated most of what it needed to demonstrate on this flight. The parking orbit systems check is the last graceful exit before the mission becomes something you finish rather than something you stop. At approximately 2 hours and 20 minutes after launch, assuming all systems are nominal, the interim cryogenic propulsion stage executes the translunar injection burn. This is the moment the mission crosses from Earth orbit to interplanetary transit. The burn fires for approximately 6 minutes and 23 seconds, accelerating the spacecraft from its orbital velocity of roughly 17,500 miles per hour to approximately 24,500 miles per hour, fast enough to escape Earth's gravitational grip and reach the Moon. The burn is precise in a way that is difficult to overstate. The trajectory the burn establishes is the trajectory the spacecraft will follow for the next 3 days. Small correction burns are possible, but the fundamental arc is set here in these 6 minutes. After the burn, the interim cryogenic propulsion stage separates. The Orion crew module and service module are now alone. No more upper stage, no more launch vehicle. Just the spacecraft and the 4 human beings inside it, moving away from Earth at a velocity that will gradually decline as Earth's gravity works against them, heading for a rendezvous with the Moon that the laws of physics have already scheduled. And the clock on the Rescue Impossible window has begun to run. In the first 12 hours after the trans-lunar injection burn, the spacecraft is still relatively close to Earth. Close in the cosmic sense, not the practical one, but close in the specific sense that the abort options are still viable. At 12 hours into the trans-lunar coast, the crew is approximately 75,000 miles from Earth. The service module engine is still capable of a return burn. The trajectory can still be bent back toward home. The window is not yet open, but the crew is already experiencing the thing that no training can fully replicate, which is the visible shrinking of Earth. This is not a metaphor. It is a literal, perceptual experience that every astronaut who has traveled beyond low Earth orbit has described in terms that are remarkably consistent across different people, different missions, different decades. In low Earth orbit, the Earth fills the window. It is enormous, curved at the edges, the terminator line between day and night sweeping slowly across the surface below you. You do not feel far from Earth in low Earth orbit because you are not far from Earth. You are above it, but you are not away from it. The entire visual experience of low Earth orbit is dominated by Earth's presence. As the spacecraft moves away from Earth on the trans-lunar coast, that changes. The Earth does not gradually recede in a way you adjust to slowly. It shrinks in increments that are perceptible during a single watch period. At 75,000 miles, it is still large enough to fill a substantial portion of the window. By 150,000 miles, it has contracted enough to feel like an object rather than a world. By 230,000 miles, the deep point of the Rescue Impossible window, it is a disk, still blue-white-brown in the sunlight, still recognizably the planet you launched from, but small enough that you could cover it with your outstretched thumb. The crew of Artemis II will have 4 windows in the Orion crew module. They are not the large panoramic windows of science fiction spacecraft. They are functional viewports, designed and sized to balance the crew's need for situational awareness against the structural requirements of a pressure vessel that has to survive re-entry. But they are enough. The crew will watch the Earth shrink, and they will know, with a precision that ground-based training cannot manufacture, exactly how far they are from help. Reed Wiseman will know. Victor Glover, the pilot who flew F/A-18S from carrier decks and spent 6 months on the International Space Station as part of Crew 1, will know. Mission specialists Christina Koch and Jeremy Hansen, Koch, who holds the record for the longest single spaceflight by a woman, Hansen, who is the first Canadian astronaut to fly a lunar mission, will know. They are all people who have spent careers training themselves to perform under conditions of irreducible risk, and they have all thought carefully about what it means to be in a spacecraft that is moving away from every possible form of external help at 2,000 miles per hour. But thinking about it and experiencing it are different things. The psychological literature on extreme isolation and confinement, the research done in Antarctica, in submarine service, in long-duration spaceflight on the International Space Station. Consistently, identifies the moment when rescue becomes subjectively impossible. Not just objectively impossible, as one of the most significant psychological transitions in any extreme environment deployment. It is the moment when the abstract risk calculation becomes an embodied, felt reality. For the Artemis II crew, that moment occurs sometime in the middle of the first day of the trans-lunar coast, as the Earth continues to shrink and the abort boundary approaches and the service module's viable return window gradually narrows to nothing. What does the crew do during these hours? This is not a dramatic question. It has a mundane and specific answer. They eat, they sleep in shifts, using sleeping bags attached to the interior of the capsule because there is not enough room for 4 people to sleep horizontally in the Orion crew module. They perform the systems checks that the flight plan schedules at regular intervals, checking carbon dioxide levels, verifying thruster response, monitoring the service module propellant load, checking the heat shield sensors, cycling through the communication systems to confirm contact with both the deep space network antennas and the backup communication paths. They exercise using resistance bands in the limited space available because microgravity begins deconditioning the cardiovascular system and the musculoskeletal system within hours of launch, and the mission is long enough for that to matter. They talk to each other, and they talk to mission control, and they do the quiet, procedural, professional work of keeping a complex machine alive in a vacuum. They also look out the windows. This is not a scheduled activity. It is simply what happens when you are in that position, and the windows are there. Every astronaut who has flown on missions beyond low Earth orbit has written or spoken about the experience of watching the Earth from a distance that makes it comprehensible as an object rather than as an environment. The overview effect, the cognitive and emotional shift that comes from seeing Earth as a whole from space, has been described extensively, but the version of it that comes at 250,000 miles is different from the version that comes at 250 miles. At 250 miles, the Earth is everywhere. At 250, 0 miles, the Earth is a place you came from. The emotional register shifts from awe at the scale of the planet to something closer to longing. The crew will not talk about longing in their public communications during the mission. They will be professional, upbeat, technically precise. They are test pilots and astronauts, trained to maintain equanimity under conditions that would destabilize most people, and they will do so. But in the mission debrief, in the books written years later, in the interviews given long after the adrenaline of the mission has faded, the crew members of Artemis II will almost certainly describe the experience of watching Earth shrink during the rescue impossible window in terms that are personal and felt rather than technical. Because that is what happens when you are that far away from the only world that has ever supported human life. At approximately 20 hours into the trans-lunar coast, the abort boundary passes. The service module no longer has the propellant load for a viable return burn. The free return trajectory is now the only path home. The rescue impossible window is open. For the next 24 hours, the following is true. If the Orion crew module suffers a catastrophic pressure loss, a breach fast enough to depressurize the capsule before the crew can don pressure suits, the crew will be dead before any signal reaches Earth. The round-trip communication delay at 250,000 miles is approximately 2.6 seconds, which means mission control would not even know about the emergency until it was already over. There is no rescue vehicle that could reach the crew in a time frame relevant to any acute failure mode. The nearest humans, the rest of humanity, all 8 billion of them, are 250,000 miles away and entirely unable to help. But here is the thing that the mission planners understood, and that is easy to lose in the drama of the rescue impossible window. The window does not make the mission more dangerous in an absolute sense. It makes it differently dangerous. The risks during the rescue impossible window are real, but they are not higher in probability than the risks during launch or during re-entry or during the lunar flyby. The window does not add new failure modes. It changes the consequent structure of the failure modes that already exist. A micrometeorite impact that would be survivable in low Earth orbit because a rescue vehicle could reach the crew within hours becomes unsurvivable in the rescue impossible window because no rescue vehicle can reach them at all. The probability of the impact does not change. Only the consequence does. This is the precise and important distinction that mission planners carry with them through every design review and every risk assessment for Artemis II. The question is never, is the rescue impossible window dangerous? The question is the risk profile of the rescue impossible window acceptable given the mission objectives and the design choices available? And the answer that NASA arrived at, after years of analysis, is yes, but only because of a specific set of design choices embedded in the Orion spacecraft and the mission architecture that work together to make the window's risk profile comparable to the risk profile of other mission phases rather than catastrophically worse. Those design choices are not accidental. They are the direct legacy of every crewed spaceflight failure in NASA's history: Apollo 1, Apollo 13, Challenger, Columbia, filtered through decades of engineering culture change and incorporated into the Orion design at the component and system level, the pressure vessel redundancy, the carbon dioxide removal system backup, the suit system design that allows the crew to operate in suits for extended periods if the cabin pressure degrades, the radiation monitoring architecture that provides enough warning of a solar particle event to allow the crew to shelter in the most shielded part of the capsule. None of these systems can rescue the crew from the rescue impossible window, but they can change the probability that any given failure mode inside the window becomes fatal rather than survivable. And the mission planners made one more decision that is not always discussed in the public coverage of Artemis II, but that is critical to understanding the window. They decided not to try to eliminate it. There were trajectory options studied that would have reduced the rescue impossible window or changed its timing. Some of them used more propellant. Some of them required a different launch window geometry. Some of them would have reduced the quality of the lunar flyby data collected during the mission. The free return trajectory with the 24-hour rescue window was not the only option. It was the best option, judged across a set of criteria that balanced mission objectives, crew safety, propellant margins, and the long-term program requirements for what Artemis III and Artemis IV will need to accomplish. That judgment is itself a statement about what the program is. Artemis is not the space shuttle program, which was designed around the assumption of routine, safe access to low Earth orbit. Artemis is not the International Space Station program, which was designed around the assumption of continuous crew presence in a well-understood orbital environment where rescue is always days away at most. Artemis is the program that goes back to the Moon and then to Mars. And the Moon and Mars are places where rescue will sometimes not be possible, where the crew will be on their own for periods that make the Artemis II window look brief, where the consequences of failure are irrevocable in ways that no ground-based intervention can change. The 24-hour rescue impossible window on Artemis II is, in this sense, not just a feature of this specific mission. It is a preview It is the first time since 1972 that NASA has put human beings in a situation where Earth cannot help them, and it is designed to be that way, to test not just the spacecraft and the trajectory, but the human and institutional ability to accept and manage the kind of risk that deep space exploration will require routinely. The crew inside that window is not just completing a circumlunar mission, they are establishing the precedent. They are demonstrating in the most concrete possible way that the gap between the world where human spaceflight happened close to Earth and the world where it happens far from Earth can be crossed, that the rescue impossible window can be managed, that the risk profile can be acceptable, that the commitment to the mission can hold even when the physics of the situation mean that holding is the only option. And that demonstration matters not just for Artemis III, which will land on the Moon, or for Artemis IV, which will begin building the lunar gateway, or for the eventual Mars missions that represent the long horizon purpose of the whole program. It matters because the window is where the program reveals what it actually is, not in the speeches, not in the budget submissions, not in the artists' renderings of astronauts standing on the lunar South Pole, in the moment when 4 human beings are 250,000 miles from Earth with no possibility of rescue, and they keep doing their jobs, and the spacecraft keeps working, and the mission continues. That is what the window is for. But the window has not closed yet. The crew is still in it. The lunar flyby is still ahead. And there are specific moments inside the window where the risk profile is not uniform, moments where the convergence of mission events and spacecraft state create brief periods of elevated exposure that the crew and mission control manage through procedures that were designed specifically for this phase of the flight. Those moments, and what happens during them, are where the story of the 24-hour window becomes most specific and most human. There is a specific hour inside the Rescue Impossible window that the flight directors at Mission Control refer to internally as the deep point. It is not a term that appears in the official mission documentation. It is not marked on the trajectory plots with a special symbol or flagged in the crew timeline with a procedural call-out. It is a piece of informal language that emerged during the simulation runs, the months of practice missions that the flight control teams ran in the year before launch, working through every failure scenario they could construct, building the muscle memory of response that would carry them through the real mission. The deep point is the moment of maximum commitment. It is the hour when the crew is furthest from the abort boundary behind them, and furthest from the lunar flyby ahead of them, equidistant in time from both the moment the rescue window opened and the moment it will close. It is the center of the 24 hours, and it is where the mission planners focused the most attention when they were deciding what risks were acceptable and what risks were not. To understand why the deep point matters, you have to understand how the risk profile of the Rescue Impossible window is not flat. It is shaped like a curve. At the moment the abort boundary passes and the window opens, the crew is moving away from their last viable emergency return option, but they are also still relatively close to Earth in terms of communication round-trip time, and still in the phase of the mission where the spacecraft systems are freshest, fewest hours of operation, lowest accumulated exposure to the space environment, highest confidence in the state of every critical component. As the window deepens, those factors gradually shift. The communication round-trip time increases slightly. The accumulated operational hours on every system tick upward. The spacecraft has been in the thermal cycling environment of deep space for longer, and the distance from Earth continues to grow. At the deep point, all of these factors are at their most unfavorable combination. The crew is as far as they will get from the abort boundary. The spacecraft has been operating in the deep space environment for the longest it will have been. The Earth is at its smallest apparent diameter in the windows, and the lunar flyby, which will end the window by pulling the spacecraft into the final phase of the free return trajectory and beginning the journey home, is still many hours away. It is during this phase that the crew executes a set of procedures that have no equivalent in any previous crewed spaceflight program. They are called Deep Point Systems Reviews, and they are exactly what they sound like. A comprehensive methodical evaluation of every critical spacecraft system conducted specifically because this is the moment in the mission when a developing problem that was not yet serious at the start of the window is most likely to have progressed to the threshold of concern. The procedures are not designed to find catastrophic failures. Those would have already manifested. They are designed to find slow degradations, the kind that develop over hours, the kind that in low Earth orbit you would address by calling the maintenance crew up on the next resupply mission or by scheduling a spacewalk. In the Rescue Impossible window, there is no maintenance crew. There is no spacewalk option for the kind of failures most likely to develop during the transit. There is only the crew, the spacecraft, and the procedures. The Deep Point Systems Review is the moment when the crew stops and asks, methodically and without rushing, whether anything about the spacecraft has changed since the last review, whether any trend in any telemetry stream is moving in a direction that needs attention, whether the consumables budget, oxygen, water, carbon dioxide removal capacity, propellant, is tracking within the expected ranges. It is, in a sense, the mission's most rigorous moment of self-examination, conducted at the moment when self-examination matters most and the options for responding to a negative finding are most limited. The carbon dioxide situation receives particular attention during the Deep Point Review. The reason is Apollo 13. In April 1970, the crew of Apollo 13, Jim Lovell, Jack Swigert, Fred Hayes, were 2 days into their trans-lunar coast when an oxygen tank in the service module exploded, disabling 2 of the 3 fuel cells that provided electrical power to the command module, and venting most of the spacecraft's oxygen supply into space. The crew survived because of a sequence of improvised responses that have become the defining case study in NASA's culture of problem-solving under impossible constraints. One of the most famous moments in that survival sequence was the construction of a makeshift carbon dioxide scrubber using materials from the lunar module, a device that the crew built from a plastic bag, cardboard, and duct tape. Because the lunar module's scrubber canisters were square, and the command module's scrubber system was designed for round canisters, and the carbon dioxide was rising to dangerous levels faster than anyone had anticipated. The Orion spacecraft was designed with the specific lesson of Apollo 13's carbon dioxide problem incorporated into its architecture. The environmental control and life support system on Orion uses a different scrubbing technology and carries redundant capacity that the Apollo command module did not have. The crew has access to backup procedures that do not require improvised construction from spare parts. The carbon dioxide monitoring system provides continuous real-time data to both the crew and mission control. None of this eliminates the risk of a carbon dioxide emergency, but it changes the response options available if the primary system degrades. What the Deep Point Review is really checking for in the carbon dioxide monitoring, as in every other system review, is the difference between a nominal trend and an anomalous one. Spacecraft systems degrade continuously. Every hour of operation accumulates wear, thermal cycling, vibration fatigue, radiation exposure. The question is never, is this system exactly as good as it was at launch? It is always, is this system still within the acceptable performance envelope for the remaining mission duration? That question has a different answer at the deep point than it does at any other time in the mission, because at the deep point, the remaining mission duration includes both the rest of the Rescue Impossible window and the 3-day return coast, and any system that is degrading at a detectable rate has to be evaluated against that full remaining timeline rather than just the immediate next few hours. The flight directors running the mission from the Christopher C. Craft Jr. Mission Control Center in Houston are working from a flight rule document that is, in aggregate, one of the most detailed operational decision frameworks ever written for a crewed spaceflight mission. The flight rules for Artemis II are not public. The full document is an internal NASA operational reference, but their structure and philosophy can be inferred from the published mission documentation and from the descriptions of the simulation process that NASA has shared publicly. For the Rescue Impossible window specifically, the flight rules encode a set of decision criteria that the flight directors use to evaluate any anomaly that occurs during the window and determine whether it represents a manageable situation or an unsurvivable one. The distinction matters because the response to a manageable anomaly during the Rescue Impossible window is categorically different from the response in any other mission phase. In low Earth orbit, a manageable anomaly triggers an evaluation of whether to continue the mission or cut it short, to bring the crew home early before the situation degrades further. During the Rescue Impossible window, cutting the mission short is not an available option. The crew is coming home on the free return trajectory regardless of what happens. The only variable is what condition they are in when they arrive. A manageable anomaly during the window therefore triggers not an abort evaluation, but a resource management evaluation. How do we preserve the crew's survival margin for the remaining mission duration, given that we cannot change the fundamental trajectory? This is a different kind of flight control than anything the mission control teams practiced before Artemis II. The shuttle program had abort modes for almost every phase of flight. The International Space Station program had emergency undocking procedures and Soyuz lifeboat protocols. The Commercial Crew program has abort modes that extend through the early orbital phase. The muscle memory of crewed spaceflight operations in low Earth orbit is built around the assumption that options exist, that the flight director's job during an anomaly is to identify and select the best option from a set of available responses. During the Rescue Impossible window, the flight director's job is different. The options are constrained by physics in a way that no decision-making framework can override. The job becomes one of optimization within a fixed envelope rather than selection among alternatives. How do we manage this anomaly in a way that keeps the crew alive until the free return trajectory brings them home? What resources can be conserved? What procedures can be modified? What can the crew do right now that improves their margin even marginally? The simulation runs showed that this shift in cognitive frame from option selection to resource optimization was one of the hardest adjustments for experienced flight controllers to make, because it required them to accept a kind of powerlessness that the culture of mission control had spent decades training them to overcome. The training for this shift was not just procedural, it was psychological. The flight control teams who trained for the Rescue Impossible window underwent sessions specifically designed to practice decision-making in environments where the most intuitive response, do something, change something, try a different approach, was not available. The lesson was not passivity. The lesson was a specific kind of active acceptance. You cannot change where the spacecraft is, but you can change how you manage the resources inside it. You cannot rescue the crew, but you can give them the best possible chance of arriving home in a condition to survive re-entry and recovery. That distinction between what is fixed and what is variable is the operational heart of the rescue impossible window, and it is relevant not just to the flight controllers, but to the crew themselves. The crew of Artemis II has been trained for the window in a way that is different from their training for any other mission phase. The launch phase training is about speed and precision. The abort scenarios develop and resolve in seconds, and the trained responses have to be automatic, executed without deliberate thought. The systems operations training is about procedure knowledge, knowing which switch does what and why, being able to troubleshoot a failure mode from first principles without the checklist if the checklist is unavailable. The rendezvous and proximity operations training, relevant if Artemis II were conducting a docking, which it is not on this mission, but which future Artemis missions will require, is about fine motor precision and spatial awareness. The training for the rescue impossible window is about something different. It is about sustained psychological function under conditions of irreducible uncertainty. The scenario runs conducted specifically for the window placed the crew in simulation environments where problems developed slowly, where the information available was ambiguous, where the correct response was not obvious and might not become obvious for hours, and where the temptation to act prematurely, to do something visible and decisive when the correct answer was to monitor and wait, was deliberately cultivated. The goal was not to make the crew comfortable with uncertainty. It was to make them capable of functioning precisely and professionally in the presence of uncertainty that could not be resolved. Christina Koch has spoken publicly about the psychological dimension of long-duration spaceflight preparation in terms that are relevant here. Her 328-day mission on the International Space Station, the longest single spaceflight by a woman at the time, required her to develop what she has described as a particular relationship with time. A way of living inside a long mission that does not treat each day as a countdown to return, but as a complete unit of work and experience in itself. That psychological posture, full presence inside the current day, rather than perpetual orientation toward the eventual end, is exactly what the rescue impossible window requires. The crew cannot spend 24 hours anxiously measuring the distance to the lunar flyby. They have to be fully present inside the window, attending to the spacecraft and each other, and the work, not mentally counting the hours until the window closes. Jeremy Hansen, the Canadian astronaut who is making his first spaceflight on Artemis II, has described his preparation for the mission in terms of a deliberate effort to internalize the risks rather than bracket them. His background includes CF-18 fighter pilot experience and years of astronaut training at both the Canadian Space Agency and NASA's Johnson Space Center, and he has spoken about the difference between knowing intellectually that a situation is dangerous and being genuinely at peace with that danger, not indifferent to it, but not controlled by it. The window is a test of that peace, not because the crew has to perform some heroic act of courage during the 24 hours, but because they have to keep doing routine professional work, in a context where the routine professional work is all that stands between them and the consequences of whatever the spacecraft chooses to do. Victor Glover, sitting in the pilot's seat, has the most specific operational responsibility during the deep point phase. His job during the window includes monitoring the navigation state of the spacecraft, verifying that the free return trajectory is tracking as expected, that small perturbations from solar radiation pressure and outgassing are within the bounds that the trajectory correction maneuver budget can address, that the spacecraft's orientation relative to the Sun is maintaining the thermal balance the systems require. These are not dramatic tasks. They are the kind of precise, continuous, attention-demanding work that test pilots are specifically selected and trained for. Maintaining situational awareness across multiple data streams simultaneously, identifying the signal of a real anomaly against the noise of normal variation, making small corrections before they become large problems. The navigation monitoring that Glover performs during the window is part of a broader picture that Mission Control is also watching. The Deep Space Network, the array of large radio antenna complexes at Goldstone in California, near Madrid in Spain, and near Canberra in Australia, provides continuous tracking of the spacecraft's position and velocity throughout the mission. The Artemis II trajectory is monitored by a team of trajectory specialists at Mission Control who are comparing the actual spacecraft state vector against the predicted one in real time and computing the magnitude of any required trajectory correction maneuver. During the rescue impossible window, these specialists are looking not just at the immediate trajectory quality, but at the longer arc question of whether the free return trajectory is intact, whether the spacecraft is still on a path that will bring it around the Moon and back to Earth at the correct geometry for the planned Pacific Ocean splashdown. If the trajectory is degraded, if the spacecraft's state vector has drifted outside the free return corridor due to an unplanned thruster firing or a navigation system anomaly, the specialists have a limited time window in which a correction burn can restore the free return path without requiring more propellant than the service module carries. Outside that time window, a trajectory degradation during the rescue impossible window becomes one of the failure modes that transitions from manageable to unsurvivable. The monitoring is therefore not routine in the sense of being unimportant. It is the continuous work of maintaining the conditions under which the free return trajectory will function as designed. This is the deeper structure of the rescue impossible window. It is not a period of waiting. It is a period of continuous active maintenance of the conditions for survival. The crew is not sitting in the dark, hoping nothing breaks. They are working systematically and professionally to keep every system within its acceptable performance envelope, to preserve every resource margin, to maintain the trajectory integrity, to monitor each other's psychological state and physical condition, to do the accumulated small tasks that the mission plan schedules during this phase and that collectively constitute the difference between a spacecraft that arrives at the lunar flyby in good condition and one that arrives degraded. The window is survivable not because survival is guaranteed, but because the people inside it are doing the work of survival continuously, hour by hour, for 24 hours, in a vehicle that was designed for exactly this purpose, and that carries within it every lesson that NASA learned from 50 years of sending human beings into space. And then, at approximately the 44th hour of the mission, 24 hours after the window opened, more or less, depending on the exact trajectory timing, the lunar flyby begins. The Moon arrives in the windows not as a gradual brightening, but as a presence. It is already visible for the last several hours of the rescue impossible window, growing in apparent size as the spacecraft closes the distance. But the transition from visible object ahead to dominant feature of the view happens in the final few hours before closest approach, and it happens fast enough to be perceptible. The Moon does not look the way it looks from Earth. From Earth, even through a telescope, the Moon has a certain flatness to it, a quality of being a disk rather than a sphere. From 10,000 miles away and closing, it has depth. The craters are not markings on a surface, they are structures, with walls that cast shadows, with central peaks that rise from flaws that fall away into darkness. The Maria, the dark basaltic plains that form the familiar features of the near side, are vast and shadowed and utterly still. The crew will have seen training imagery of the Moon from close approach distances. They will have studied the surface in the context of the Artemis program's long-term objectives, familiarizing themselves with the geology and the geography of the lunar South Pole region, where the eventual crewed landings will occur. But the direct visual experience of the Moon at close range, from inside a spacecraft that is moving at thousands of miles per hour relative to the lunar surface, is something that the training imagery cannot approximate. It is the Moon as a world, rather than the Moon as an image, and it comes at the end of 24 hours in the rescue impossible window, when the crew is tired and they have been doing the careful maintenance work of the deep point review and the systems monitoring for an entire day, and it comes in the windows like a wall. The closest approach, the perisyntheon, will bring Orion to approximately 4,600 miles above the lunar surface. This is closer than the Moon's radius. The crew will be close enough that the curvature of the Moon fills the windows, that the horizon is visibly curved, that the speed of their transit relative to the surface is perceptible as the surface moves beneath them. The flyby lasts approximately 2.5 hours from first close approach to the point where the Moon's gravity has done its work, and the spacecraft is on the outbound leg of the free return arc, now aimed back at Earth. Those 2.5 hours are, in a specific and important sense, the close of the rescue impossible window. Not because the window closes the moment the flyby begins, it does not, but because the lunar flyby is the event that commits the spacecraft to the return trajectory. And once the spacecraft is on the return trajectory, the abort calculus changes. The return trajectory itself becomes the path home, and mission control's job transitions from preserving the conditions for a free return to monitoring the approach to re-entry and preparing for the final phase of the mission. The rescue impossible window does not close with a signal or a call-out from mission control. It closes the way it opened, not with drama, but with the accumulated arithmetic of position and velocity. One moment the spacecraft is at a position where no return burn is viable. The next moment it has moved far enough along the free return arc that the return trajectory itself is carrying it toward Earth at a velocity and angle that will bring it home. The window closes in the math before it closes in the mind, but when it closes, something changes for the crew. Not relief exactly, they are professionals. And the mission still has 3 days of return coast and a re-entry that carries its own risks. But something. A shift in the psychological weight of their position. The Earth in the windows is no longer a disk they are moving away from. It is a destination they are moving toward. The distance is still 250,000 miles, still far beyond any possibility of quick rescue, still measured in the kind of numbers that resist emotional comprehension. But it is decreasing rather than increasing, and the direction of travel has changed, and the crew knows it. The deep point is behind them. The window is closing. They are coming home. But what they are coming home to and what the mission means for everyone who comes after them is a story that has not yet been told. And it begins in the last hours of the rescue impossible window, in the moment when the moon is in every window and the crew is as far from Earth as any human being has been since 1972. And the thing they are actually doing is not surviving. It is deciding what comes next. There is a photograph that does not exist yet. It will be taken sometime during the Artemis II mission, probably during the rescue impossible window, probably by one of the 4 crew members using a camera pressed against one of the Orion viewports. It will show the Earth from a distance of somewhere between 230,000 and 270,000 miles. The Earth will be small in the frame, a disk, blue and white and brown, surrounded by the absolute black of space. It will not be the first photograph of Earth from that distance. The Apollo missions produced dozens of them. The most famous, Earthrise, was taken by Bill Anders during Apollo 8 in December 1968 as the command module came around the far side of the moon and the crew saw the Earth rising above the lunar horizon for the first time. Another, taken by the Apollo 17 crew, became known as the Blue Marble and became one of the most reproduced photographs in human history. The photograph that the Artemis II crew takes will be different from those not because the Earth will look different. It will look essentially the same blue-white disk, the same swirl of cloud cover over the same oceans, but because of what will be absent from it. In the Apollo photographs, everything outside the Earth was unknown territory. The photographs were taken during missions that were exploring a destination humanity had never reached. The crew taking those photographs did not know what came next, not in the deep programmatic sense, because no one did. Apollo was finding out. The crew of Artemis II will know what comes next. They will have been briefed on the Artemis III mission that will land on the moon, probably within 2 years of their flight. They will know the landing site candidates at the lunar South Pole, the craters near the Shackleton de Gerlache Ridge, where the permanent shadow regions hold water ice that could sustain a long-term human presence. They will know the names of the astronauts in training who might walk on that surface. They will know the broad outlines of the lunar gateway station that will eventually orbit the moon and serve as a staging point for surface expeditions. They will have spent years working on a program whose trajectory they understand in a way that the Apollo astronauts, working in a program that was discovering its own shape as it went, could not. This knowledge changes what the photograph means. The Artemis II Earth photograph, whenever it is taken, is not a picture of an origin point seen from unexplored territory. It is a picture of an origin point seen from a corridor, a path that has been surveyed, that will be travelled again. That is the beginning of a route rather than the beginning of an adventure. The distinction matters because it tells you something about what the rescue impossible window represents in the longer arc of the program. The 24 hours that the Artemis II crew spends beyond the reach of rescue is not the climax of the story. It is the proof of concept. It is the demonstration that the corridor is passable, that the risk profile is acceptable, that human beings can occupy this region of space for this duration and return. If the demonstration succeeds, and the entire architecture of the Artemis program is built on the assumption that it will, the corridor becomes routine. Not safe in an absolute sense, never that, but routine in the operational sense. The flight control teams will have run the window once with real human beings and real spacecraft and real consequences, and the lessons from that run will be incorporated into the flight rules and procedures for every subsequent mission. The 24 hours that feel singular and irreducible in the context of Artemis II will become one phase among many in the operational template for cislunar human spaceflight. This is how risk becomes managed rather than eliminated. Not by removing the rescue impossible window from the trajectory, the physics does not allow that, but by accumulating the knowledge and the institutional confidence that comes from running the window successfully, repeatedly, until the flight controllers and the crews develop the same relationship with the deep point that submarine crews develop with deep dives, or that polar researchers develop with winter over isolation, or that the early jet test pilots developed with the sound barrier. The thing that seems categorically dangerous becomes categorically understood, and categorical understanding changes the texture of the risk, even when it does not change the probability of a catastrophic failure. But that accumulated confidence does not exist yet. It will not exist until after Artemis II. Right now, in this mission, in this window, the 4 crew members of Orion are doing something that no one has done since 1972, and that will not feel routine, regardless of how well they have prepared. Because the first time is always different from every subsequent time. The first time, the knowledge that you are in a situation where no one can help you is not a managed fact. It is a lived reality. And lived reality has a texture that preparation cannot fully anticipate. Let us stay inside the capsule for a moment. Let us be specific about the physical environment that the crew occupies during the rescue impossible window, because the physical reality of their situation is part of what makes the 24 hours what it is. The Orion crew module is approximately 16.5 feet in diameter at its widest point and approximately 10.8 feet tall. The pressurized volume, the space actually available for the crew to occupy, is approximately 316 cubic feet. This sounds like a number rather than a feeling until you compare it to something you can imagine. It is approximately the size of the interior of a full-size Chevy Suburban SUV, but in 3 dimensions rather than the flat floor plan of a car. For 4 adult human beings in spacesuits during critical mission phases and in lightweight clothing. During the quieter phases of the translunar coast, 316 cubic feet is not cramped in the way a closet is cramped, but it is intimate in a way that no amount of crew selection and psychological screening can fully prepare you for. In microgravity, the 3-dimensional nature of the space becomes more accessible. You can float above the seat level and use the upper portions of the cabin that would be wasted volume in a gravity environment. The crew can position themselves at different points in the cabin, creating the functional equivalent of personal space, even in a volume that would not support it in a ground environment. But they are still 4 people in a space that is, by the standards of any other human environment, extremely small. They can hear each other breathing. They know when another crew member is not sleeping well. The intimacy of the space is total in a way that is different from any other professional environment, including the International Space Station, where the pressurized volume is approximately 32,000 cubic feet, more than 100 times larger, and crew members can genuinely be alone. On Orion during the translunar coast, you are never alone. This is not a complaint. The crew was selected partly for their ability to function in close quarters over extended periods, and the dynamic among Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen has been deliberately cultivated through years of shared training. They know each other. They trust each other. The interpersonal texture of the crew module during the rescue impossible window is not that of 4 strangers trapped together. It is that of 4 highly trained professionals who have spent years preparing for exactly this moment and who are now, finally, doing the thing they prepared for. But the intimacy of the space still has effects that no training fully controls. Sleep is the most significant one. The crew sleeps in shifts during the trans-lunar coast because there is not enough volume for 4 people to sleep simultaneously in any comfortable configuration, and because the mission plan requires at least 2 crew members to be alert at any given time. The shift schedule means that the rescue impossible window spans multiple sleep-wake cycles for each crew member, and the quality of sleep in microgravity in a pressurized capsule is never equivalent to sleep on the ground. The ambient noise of the life support system, the temperature variations as the spacecraft rotates slowly to distribute solar heating, the subtle but continuous sensory signals that the vestibular system receives in microgravity and does not know how to interpret, all of these affect sleep quality in ways that are cumulative over a multi-day mission. By the deep point of the rescue impossible window, roughly 12 hours after the window opened and 12 hours before it will close, every crew member is carrying a sleep debt, not a debilitating one. The mission plan accounts for this, and the scheduling of critical procedures is timed to align with periods when crew alertness is expected to be highest, but a real one. The cognitive effects of accumulated sleep deprivation in spaceflight are well documented from the International Space Station Research Program. Reaction time degrades, working memory capacity decreases. The ability to detect subtle anomalies in a data stream, exactly the kind of monitoring that the Deep Point Systems review requires, is reduced compared to a fully rested baseline. The crew knows this. Mission Control knows this. The procedures during the deep point phase are designed with this degradation factored in, allocating more time for reviews that would take less time with a fully rested crew and building in explicit verification steps that a rested crew might perform more automatically. The food situation is also worth dwelling on, because it sounds mundane, and it is mundane, and the mundane details of what the crew eats and drinks during the rescue impossible window are part of what makes the window real rather than abstract. The Orion spacecraft carries food and water for the full mission duration plus margins for an extended mission if the return is delayed. The food is the rehydratable and thermostabilized food technology that has been used in spaceflight since the Apollo program, refined through the shuttle program and the International Space Station experience to the point where it is nutritionally complete and not entirely unpleasant to eat. It is not good in the way that food on Earth is good, but it is sufficient. The crew drinks water from a system that recycles moisture from the cabin air and supplements it from stored water supply. The water tastes like water. These are small dignities in an environment that does not offer many. The bathroom situation is less dignified, and the crew knows going in that it will not be. The Orion Waste Management System is a direct descendant of the systems used on the Space Shuttle, with improvements informed by the International Space Station program, but it is still the kind of thing that the training documentation describes in clinical language that somewhat understates the reality. In microgravity, the management of human waste is a procedural task that requires attention, equipment, and a matter-of-fact approach to bodily functions that civilian life does not cultivate. The crew has trained for it, they manage it professionally, but it is part of the lived texture of the rescue impossible window in a way that the press releases about the mission do not fully convey. These details matter not because they are dramatic, but because they are the opposite of dramatic. They are the ordinary human functions that continue regardless of where you are or what is at stake. And their continuation inside the Rescue Impossible window is part of what makes the window survivable in the psychological sense, as well as the technical one. The crew is not transcendent during these 24 hours. They are not heroic in a way that suspends their ordinary human needs. They are four people doing a very difficult and very unusual job while also eating rehydrated food and sleeping in shifts and managing the waste management system and hearing each other breathe, and the ordinary human texture of those 24 hours is what makes the extraordinary technical context of those 24 hours something that human beings can actually occupy rather than just endure. Victor Glover has spoken publicly about the experience of his 6-month stay on the International Space Station in terms that emphasize the normalization of the extraordinary environment, the way that what begins as overwhelmingly novel gradually becomes the known context within which ordinary life continues. He described the view of Earth from the cupola of the station not as something that stayed stunning throughout the mission, but as something that became, over time, the background against which he did his work and lived his daily life. The awe did not disappear, but it became compatible with eating breakfast and exercising and doing the laundry equivalent in space, and missing his family, because human beings are adaptive in that way. And the adaptation is not a diminishment of the experience, but a deepening of it. The Rescue Impossible window is too short for that kind of normalization. 24 hours is not enough time for the extraordinary to become background, but it is long enough for the crew to find their footing inside it, to develop the working relationship with the unusual reality of their position that allows them to function without being consumed by it. By the deep point of the window, they are not overwhelmed. They are busy, and being busy in a purposeful way, doing the systems reviews, monitoring the telemetry, eating and sleeping and managing the spacecraft is its own form of psychological stability. Mission Control is busy too, and the specific texture of what Mission Control is doing during the Rescue Impossible window is worth understanding. Because the relationship between the crew and the ground during these 24 hours is different from the relationship during any other mission phase, and that difference has been deliberately designed into the communication protocols. The flight controllers in Houston cannot rescue the crew during the window. This is the foundational fact of the communication relationship during this phase, and it shapes everything about how Mission Control operates. In low Earth orbit operations, the implicit model of the Mission Control relationship is one of active intervention capacity. The ground has options. The ground can send instructions that change the crew's situation in a material way. The ground's monitoring is not just informational but actionable in a direct sense. During the Rescue Impossible window, that model is suspended. The ground can see everything. The ground can communicate with the crew in near real time, with only the 2.6-second round-trip delay that the distance imposes. But the ground cannot change the crew's physical situation. It cannot send help. It cannot alter the trajectory. It can only provide information and support. This changes the psychological dynamic in ways that the flight control teams worked through extensively during the simulation runs. The temptation, when monitoring a crew in a situation where the ground cannot intervene effectively, is to over-communicate, to fill the communication channel with information and instructions and reassurance in a way that compensates for the ground's sense of helplessness. The simulation runs showed that this tendency, if unchecked, created a cognitive burden on the crew that degraded their performance on the spacecraft management tasks that were actually within their control. The flight rules for the rescue impossible window therefore specify a communication discipline, a deliberate limitation on the volume and frequency of ground-to-crew communications during non-emergency periods, preserving the crew's cognitive bandwidth for the work they need to do, and respecting their professional autonomy in a situation where their professional autonomy is more absolute than it has been for any crewed mission since Apollo. The communication discipline is not silence. Mission control is never silent during a crewed mission. The flight directors and the flight controllers who staff the consoles in Mission Control Center, the guidance, navigation and control officer, the environmental and life support officer, the propulsion officer, the flight surgeon, the communications officer, are all monitoring their specific domains and are ready to communicate relevant information to the crew at any point. But the cadence and the content of communications during the rescue impossible window is shaped by the recognition that the crew is not waiting for instructions from the ground. They are conducting the mission. The ground is watching. There is a word that the flight control culture uses for this dynamic, and it is a word that does not often appear in the public narrative about mission control, which tends to emphasize the ground's active role in managing crewed missions. The word is trust. During the rescue impossible window, mission control's primary function is not management, it is trust. The crew has been trained for this, the spacecraft was built for this, the mission was designed for this. The ground's job during the window is to trust that the preparation was adequate and to be ready to provide whatever support is meaningful if something changes. That trust is not passive. It is active in the sense of being continuously renewed by the monitoring data, by the telemetry streams that confirm the spacecraft is functioning within acceptable parameters, by the voice communications that confirm the crew is alert and professional and working, by the trajectory data that confirms the free return path is intact. Every time a piece of monitoring data comes in, and it is nominal, the trust is renewed. And every renewal of the trust is a small act of acceptance, an acknowledgement by the people on the ground that the situation is what it is, that the crew is where they are, that the physics of the window cannot be negotiated with. This is the ground's version of the psychological work that the crew is doing inside the capsule. The crew is managing their own responses to the irreducible fact of their position. The ground is managing its own responses to the irreducible fact of its limitations. Both forms of management are professional, trained, and deeply human, and both are necessary for the mission to succeed. There is another presence in the mission that is worth acknowledging during the rescue impossible window, and that is the presence of everyone who came before. The Apollo crews, whose missions established the baseline knowledge of what the cislunar environment does to spacecraft and to human bodies. The engineers who designed the systems that Orion's architecture draws on. The astronauts who died in Apollo 1, in Challenger, in Columbia, whose deaths changed the culture of NASA in ways that are embedded in the design of every system on the Orion spacecraft, in the flight rules that govern every decision during the mission, in the values that the flight control teams carry into the Mission Control Center every time they sit down at their consoles. The rescue impossible window exists in the context of all of those people and all of that history. The 24 hours is not a fresh start. It is a continuation of a project that began in the late 1950s and that has been shaped by every success and every failure since then. The Artemis II crew is not the first to face the arithmetic of distance and consequence. They are the first to face it in this specific vehicle, on this specific trajectory. But they carry with them the accumulated wisdom of everyone who faced it before, and they are supported by institutions and technologies and operational practices that did not exist when the Apollo crews flew. This does not make them safe, it makes them prepared. And prepared is what the rescue impossible window requires. At approximately hour 40 of the mission, 4 hours before the window closes, 4 hours before the lunar flyby begins in earnest, the moon is large enough in the windows that the crew can see individual large craters without optical aids. Tycho, in the southern highlands of the near side, is visible as a bright-rayed impact structure with a distinctive central peak. Mare Tranquillitatis, the Sea of Tranquility, where Apollo 11 landed, is a dark expanse that the crew recognizes from maps and training imagery, but that looks different from this distance and this angle than it does in any two-dimensional representation. The crew can see the curvature of the lunar limb against the black of space. The spacecraft is accelerating now, pulled by the moon's gravity, moving faster than it has moved since the first hours after the trans-lunar injection burn. The approach to Pericynthion, the closest point of the flyby, is not something you feel in any visceral sense in a spacecraft. There is no wind noise, no sensation of speed, no G-force of turning. The only evidence of the acceleration is in the navigation display, where the velocity readout is climbing in numbers that are precise and calm and carry within them the entire physics of what is about to happen. The crew checks their suits, they verify the pressure seals, they confirm the hatch integrity. They run through the Pericynthion procedures one more time, not because they have not done it a dozen times already, but because at this point in the mission, in this phase of the approach, the procedural verification is itself a form of stability. The checklist is the anchor. The anchor holds. The moon fills the windows. And somewhere in that approach, the rescue impossible window closes, not with a sound or a signal, with the mathematics of position and velocity, silently, as the spacecraft crosses the threshold into the geometry of return, and the free return trajectory asserts itself as a real and certain path home. The window closes the way death's absence closes when the danger has passed, not dramatically but completely, and with a weight that is felt before it is understood. The crew is past the deep point, the window is behind them. Ahead is the moon, and beyond the moon 3 days of return coast, and beyond that the Pacific Ocean and the recovery fleet and the world they left. But before all of that, there is something else. There is the far side. There is a moment during the Artemis II lunar flyby when all 4 crew members will lose contact with Earth simultaneously, completely, and without any possibility of re-establishing it until the geometry of their trajectory carries them back around to the near side of the moon. The moment is called loss of signal. It has been planned for. It appears in the mission timeline as a scheduled event bracketed by pre-LOS procedures and post-LOS procedures, annotated with the expected duration, treated in the operational documentation with the same calm procedural language that describes every other phase of the mission. It lasts approximately 25 minutes. 25 minutes of absolute silence. No telemetry streaming to mission control. No voice communication with the flight directors, no navigation uplinks from the deep space network, no contact with any human being outside the spacecraft. The 4 crew members of Artemis II will pass behind the Moon into a region of space where the Moon's bulk sits between them and every antenna on Earth, and for 25 minutes they will be more isolated than any human beings alive. More isolated in the strict communicative sense than anyone on the International Space Station, anyone on a research station in Antarctica, anyone on a submarine at depth, anyone anywhere on or near Earth. The Moon will be between them and the rest of humanity, and the silence will be total. This is not the Rescue Impossible window. The Rescue Impossible window closed as the lunar flyby began, as the free return trajectory asserted itself, and the spacecraft crossed the threshold into the geometry of return. The loss of signal occurs during the flyby itself, after the window has technically closed, as the spacecraft swings around the Moon at its closest approach and briefly disappears behind the lunar far side. By the time loss of signal occurs, the crew is already on the arc that will bring them home. The physics of their situation has changed fundamentally from the deep point. They are coming back, but the silence is still the silence, and the 25 minutes behind the Moon are the most complete expression of what the entire mission represents, the most literal version of the thing that the Rescue Impossible window only approximated. In the window, the crew was beyond rescue. Behind the Moon, the crew is beyond communication. The two are different, but they rhyme. And the 25 minutes behind the Moon is where the full weight of what the Artemis program is attempting becomes something you can hold in your hands and examine. Let us examine it. The far side of the Moon is the most alien place a human being has ever been, with one narrow exception. The exception is the Apollo missions that also went behind the Moon, Apollo 8, 10, 11, 12, 14, 15, 16, and 17, all of which sent their crews around the lunar far side during their orbital phases, all of which experienced the loss of signal that Artemis II will experience. The Apollo crews were there first, but the Apollo crews were last there in December 1972, and the 50-plus years since then have not included a single human being who has been behind the Moon, out of contact with Earth, in a spacecraft traveling at thousands of miles per hour over a surface that no human eye has seen directly, except in those brief mission windows. The Artemis II crew will be the first people to see the lunar far side with their own eyes since Harrison Schmitt looked out the window of the Apollo 17 command module during the return coast in 1972. That fact has a weight to it that is difficult to convey in the language of mission planning and flight rules and risk profiles. It is the kind of fact that belongs to a different register, the register of human experience, of what it means to be in a place, of the irreducible difference between knowing something and seeing it. The lunar far side does not look like the near side. The near side, the face of the Moon that is always turned toward Earth due to the tidal locking of the lunar orbit, is characterized by the large dark Maria, the ancient basaltic plains that formed when volcanic activity flooded the low-lying impact basins billions of years ago. The near side is the Moon of human mythology and art and poetry, the Moon that has been watched and named and given meaning by every human culture in history. The far side has none of that. It has never been visible from Earth. It was not seen by any human eye until 1959, when the Soviet Luna 3 spacecraft photographed it for the first time. What the photographs revealed was a surface that was almost entirely highland terrain, heavily cratered, with almost no Maria. The volcanic flooding that shaped the near side did not reach the far side. The reasons for this asymmetry are still not fully understood, which makes the far side not just alien but mysterious in a way that the near side, mapped and studied for centuries, is not. From 4,600 miles above the surface at closest approach, the crew will see this landscape directly. The craters of the far side highlands are some of the most ancient surface features in the solar system, impact structures that formed in the first billion years of the Moon's history, preserved by the absence of the geological activity that reshaped the near side. Some of them are large enough to be visible from 4,600 miles without optical aids. The South Pole Aitken Basin, the largest confirmed impact structure in the solar system, approximately 1,600 miles in diameter and more than 5 miles deep, will be partially visible during the flyby. It is not just a crater. It is a scar of cosmic violence so large that it exposed the lower crust of the Moon, preserving a geological record that scientists have been trying to sample and study for decades, and that the Artemis program's eventual surface missions are specifically designed to access. The crew will photograph what they see. That is part of the mission. The Orion spacecraft carries a suite of cameras that will document the flyby, and some of those cameras will be operated by the crew during the far side transit. But the documentation is not the point. Or not only the point. The point is that human beings will be there, with eyes, seeing a landscape that has been seen by instruments and by the cameras of robotic spacecraft, but never by a person in the way that a person sees, with the embodied presence that changes what seeing means. The crew of Apollo 8 were the first people to see the lunar far side, and Frank Borman, Jim Lovell, and Bill Anders have all described the experience in terms that suggest it was different from any image they had seen beforehand, different in quality and in emotional register, different in the way that being somewhere is always different from knowing about somewhere. The Artemis II crew will experience this during the 25 minutes of loss of signal, cut off from Earth, alone with the Moon and each other and the silence of the radio. They will be the first people in over 50 years to have that experience, and they will have it at the end of a 24-hour rescue impossible window, exhausted and alert, carrying the accumulated psychological weight of everything the window required of them. The 25 minutes behind the Moon will be the quietest and most complete version of the isolation that the entire mission represents. The full stop at the end of the sentence, "The rescue impossible window began." Then the spacecraft will swing around the lunar limb and the Earth will appear in the windows. This is the moment that every Apollo crew has described as the most profound of their missions, more profound than the landing for those who landed, more lasting in its emotional residue than anything else the missions produced. The Earth appearing from behind the Moon after loss of signal is not just the restoration of communication and the visual confirmation that the return trajectory is intact, it is the return of orientation. The reappearance of the one fixed point in the entire experience that means home in the deepest possible sense of that word. The crew of Apollo 8 saw it first on Christmas Eve of 1968 as they completed their fourth orbit of the Moon, and the Earth rose above the lunar horizon, a blue and white sphere, small and fragile and extraordinary, hanging in the black above a grey and ancient surface. Bill Anders took the photograph that became Earthrise. Frank Borman, looking at the same view, said quietly to his crewmates that it was the most beautiful thing he had ever seen. The Artemis II crew will not be in lunar orbit. They will be on a flyby trajectory. And the geometry of their approach means the Earth will appear not as a rising object above a lunar horizon, but as a sphere visible through the window. As the spacecraft completes the swing around the far side and begins the outbound leg of the free return arc, the exact appearance will depend on the lighting geometry at the time of the flyby, but the fact of the Earth's reappearance, the moment when the radio's silence ends and Mission Control's voice comes through the speakers and the telemetry streams resume and the entire support structure of human civilization is present again in the spacecraft, that moment will be the same. The isolation ends. The return begins in earnest. Mission Control, during the 25 minutes of loss of signal, will have been doing something specific. Not panicking, not watching the clock with increasing anxiety. Working. The flight controllers will have been running through the post-LOS procedures, preparing the communication restoration sequences, verifying the predicted acquisition of signal timing against the trajectory data, ensuring that the first communication after signal restoration covers the highest priority information, confirmation of spacecraft state, crew status, any anomalies that occurred during the far side transit that the crew needs to report. The discipline of Mission Control's 25 minutes of silence is not the discipline of waiting. It is the discipline of preparing for the moment when the waiting ends. When the signal is restored, the conversation between the crew and Mission Control will be professional, precise, and layered with a subtext that neither party will articulate directly. The subtext is, "We are here, you are there, the window is behind you, the moon is behind you, the trajectory is intact, and you are coming home." That subtext does not need to be said because it is present in every exchange, in the tone of the capsule communicator's voice, in the crew's responses, in the collective exhale that the Mission Control room will permit itself, quietly, before returning to the work of managing the return coast. The return coast takes approximately 3 days. It is, in structural terms, the mirror image of the outbound coast. The same phases, the same monitoring requirements, the same sleep schedule, the same food and water management and systems reviews. But it is not psychologically the same because the direction of travel has changed, and that change is everything. The Earth in the windows is growing rather than shrinking. Each hour brings the spacecraft measurably closer to the Pacific Ocean and the recovery fleet. The distance numbers on the navigation display are counting down rather than up. The mission is resolving. This resolution is itself a kind of countdown, and it is worth dwelling on because it is where the Artemis II mission rejoins the larger countdown that the whole program represents. The 24-hour rescue impossible window was not the point of the mission, it was a phase of the mission, the most operationally significant phase from the perspective of risk management and human endurance, but a phase. The point of the mission is the data it produces, the precedents it sets, the confidence it builds, and the specific demonstration it provides to every decision-maker in the space agencies and governments and commercial entities that are watching that a crude cislunar trajectory is survivable, that Orion performs as designed, that human beings can occupy the rescue impossible window for 24 hours and emerge from it functional, healthy, and ready to do it again. The data the mission produces is extensive and specific. The Orion spacecraft carries a suite of sensors that are monitoring not just the spacecraft systems, but the deep space environment, the radiation environment beyond Earth's protective magnetosphere, the micrometeorite flux in cislunar space, the thermal environment at different phases of the trajectory. This data will inform the design of the Lunar Gateway Station, the surface habitat systems for the eventual lunar South Pole base, the life support architecture for the Mars transit vehicles that represent the program's long horizon objective. The Rescue Impossible window is itself a data collection opportunity because 24 hours of crew physiological monitoring in the deep space environment beyond the abort boundary provides information about what that environment does to human bodies that cannot be obtained any other way. The radiation data is particularly important. Earth's magnetosphere, the magnetic field that deflects the solar wind and the galactic cosmic radiation that would otherwise bombard the surface continuously, extends to approximately 40,000 miles above Earth's equator on the sunward side. Beyond that boundary, the radiation environment is different from anything experienced in low Earth orbit, where the magnetosphere still provides significant shielding. The International Space Station operates inside the magnetosphere. The Rescue Impossible window at 250,000 miles from Earth is far outside it. The crew is exposed to the full flux of galactic cosmic radiation and any solar particle events that occur during the mission window. NASA has managed this exposure in the mission design by timing the launch to avoid periods of peak solar activity and by incorporating radiation monitoring systems in the Orion spacecraft that provide real-time exposure data to both the crew and mission control. The suit systems include a provision for emergency radiation shelter, a procedure in which the crew moves to the most shielded portion of the capsule in the event of a major solar particle event. But the baseline radiation exposure during the 10-day mission is higher than anything accumulated in low Earth orbit, and the data from the crew's dosimetry during the Rescue Impossible window in particular will be used to refine the radiation exposure models that are driving the design of shielding systems for future long-duration missions. This is the practical dimension of what the window produces. But there is another dimension, less quantifiable and more important in the long run, which is the institutional confidence that comes from having run the window with real human beings and real spacecraft, and having it work. The history of human spaceflight is a history of programs that were held back, not by engineering limitations, but by institutional risk tolerance, by the accumulated weight of previous losses and the organizational cultures those losses created. After Apollo 1, NASA became more conservative about launch schedules and less willing to accept design compromises under schedule pressure. After Challenger, NASA became more careful about launch commit criteria and the culture of organizational silence that had allowed known problems to be downplayed. After Columbia, NASA rebuilt its safety culture around the principle that dissent about safety concerns must be heard and addressed rather than managed away. Each of these losses made the program more careful, and more careful programs take longer and cost more and sometimes never get back to the frontier they were exploring when the loss occurred. The Artemis program is the attempt to get back to the frontier, not to the specific frontier of the Moon, which was abandoned after Apollo 17, but to the larger frontier of human spaceflight beyond low Earth orbit, the frontier where rescue is sometimes impossible, where the physics of distance impose constraints that no amount of engineering can fully engineer around, where the crew is genuinely on their own in a way that the International Space Station never required. Getting back to that frontier requires the institutional confidence to put human beings in the Rescue Impossible window and accept the risk, and that confidence can only be built by actually doing it. Artemis II is the doing, and if it succeeds, when it succeeds, because the program is built around the expectation that it will succeed, the institutional confidence it produces will be the foundation for every subsequent mission that pushes the frontier further. Artemis III which will land on the Moon, will have a rescue impossible window of its own, and it will also have the precedent of Artemis II. The lunar landing crew will know that Wiseman and Glover and Koch and Hansen ran the window and brought the spacecraft home, and that knowledge will not eliminate the risk of the landing mission's own impossible window, but it will change the texture of how that risk is carried. The precedent is a form of company in a situation that would otherwise be utterly singular. This is what the long countdown of the Artemis program is building toward, one mission at a time. Not just the technical infrastructure of a return to the Moon, the Orion spacecraft, the Space Launch System, the Lunar Gateway, the Human Landing System, but the operational and institutional infrastructure of a program that can sustain human presence in the deep space environment over a multi-decade timeline. The Rescue Impossible window is not an obstacle to that program. It is a proof point. It is the moment when the program demonstrates that it can do the thing that the Moon and Mars require, that the risk profile is manageable, that the human beings and the institutions behind them are ready. The return coast passes. The Earth grows in the windows. The crew performs the systems reviews that will confirm the spacecraft is ready for re-entry. They stow loose equipment, verify the heat shield sensors, check the parachute system status, run through the entry interface procedures that will govern the final hours of the mission. The procedural rhythm of the return coast is different from the outbound coast, not in its content, but in its direction. Every task moves the spacecraft and the crew closer to the moment when the re-entry begins and the last, most violent phase of the mission unfolds. Re-entry is its own gauntlet. The Orion spacecraft enters the Earth's atmosphere at approximately 25,000 miles per hour, decelerating through a process that generates temperatures of approximately 5,000 degrees Fahrenheit at the heat shield. The plasma of superheated air around the spacecraft produces a communications blackout, a loss of signal that mirrors the loss of signal behind the Moon but is caused by ionization rather than geometry and lasts approximately 4 minutes rather than 25. During those 4 minutes, mission control cannot see the spacecraft. The crew cannot communicate with the ground. The heat shield is either working or it is not, and there is nothing anyone can do in either case except wait for the blackout to end. When the signal is restored after re-entry blackout, the spacecraft will be in the lower atmosphere. The parachutes will deploy in sequence. The drogue shoots first to stabilize and slow the capsule, then the 3 main parachutes to bring it to a landing speed of approximately 20 miles per hour at splashdown. The recovery fleet, Navy ships positioned in the Pacific Ocean at the predicted splashdown point, will be watching the parachutes descend. The swimmers will be in the water before the capsule touches down, ready to attach the flotation collar that prevents the capsule from sinking, ready to assist the crew out of the hatches and into the recovery vehicles. The crew will emerge into sunlight and salt air, and the noise of helicopter rotors, and the visible relief of hundreds of people who have spent 10 days watching telemetry data and waiting. They will have been in the Orion crew module for 10 days. They will be physically weakened by the deconditioning effects of microgravity, temporarily unsteady on their feet in the 1G environment of the recovery ship's deck, blinking in natural sunlight that their eyes have not experienced since the launch pad. They will be checked by the flight surgeons. They will be given fresh fruit. They will call their families. And somewhere in the first hours after recovery, before the formal debriefs begin, before the press conferences and the ceremonies and the speeches, there will be a moment for each of them when the full weight of what they did settles into place. Not the technical achievement, which is significant, not the scientific data collected, which is valuable, but the simple fact of what they were for 24 hours in a spacecraft in deep space, the only people alive who were beyond the reach of any possible help, doing their jobs, keeping the spacecraft alive, watching the Earth shrink in the windows and the moon grow and the Earth appear again, coming home. They will have been in the rescue impossible window. They will have passed through it. And on the far side of it, the program they are part of will have changed, because programs are made of precedents. And the precedent Artemis II establishes is the one that every subsequent mission will stand on. The precedent that the window is survivable, that the risk is acceptable, that human beings can go to places where rescue is impossible and come back, not because the universe cooperated or the odds broke in their favor, but because they prepared, and the people who built the spacecraft prepared, and the people watching from the ground prepared. And preparation is what you do when the thing you want to reach requires you to accept consequences that you cannot engineer away. The countdown that matters is not the one that ends with splashdown. It is the one that begins there, because after Artemis II, the next mission goes back to the moon, and the one after that lands, and the one after that begins building the infrastructure for permanent human presence on the lunar surface. And after the moon eventually, the missions that leave for Mars will leave from a program that has already proven on a trajectory around the moon in the early years of this decade that the rescue impossible window is not the end of the story. It is the beginning. The window has always been there. The distance between Earth and everything worth reaching in the universe has always included a phase where no one can follow. The physics has not changed and will not change. What changes is whether humanity is willing to go anyway, knowing what the window means, accepting the 24 hours as the price of the thing on the other side. Artemis II says yes. And the universe, indifferent as always to human courage or human loss, continues its own countdowns. The star that will expand in 5 billion years to swallow the Earth. The galaxy that will merge with ours in 4 billion years. The last star that will exhaust its hydrogen in 100 trillion years. The final black hole that will evaporate in 10 to the power of 100 years, long after the last trace of every mission ever flown has dispersed into the cold and expanding dark. Against those timelines, 24 hours is a duration so small it cannot be measured. The rescue impossible window of Artemis II is a moment in the life of a species that has not yet been alive long enough to constitute a moment in the life of the universe, and yet it matters. It matters the way all human things matter, which is not in proportion to their cosmic scale, but in proportion to what they cost, and what they build, and what they make possible. The crew of Artemis II will spend 24 hours in a window where no one can reach them, and they will come home. And what they bring back with them will be more than data and more than precedent. It will be the demonstrated fact that the distance is crossable, that the thing on the other side of the impossible window is not just theoretically reachable, but actually reached by actual people, in an actual spacecraft, in the actual present, and not some imagined future. The window closes. The Earth grows in the windows. The countdown continues. It has always been continuing.